In today's talk, I would like to discuss characterizing crack growth in Scalmalloy. The requirements for the airworthiness certification of military aircraft are delineated in the U.S. Joint Services Structural Guidelines, JSSG 2006, and the United States Air Force Mil Standard 1530D. However, for additively manufactured airframes, the certification requirements are spelt out in USAF Structures Bulletin EZ 1901. The damage tolerance and durability requirements for space applications are given in NASA Handbook 1510. The durability and damage tolerance, or DADT analysis, requires a building block approach as spelled out in Mil Standard 1530D and JSSG 2006. However, Section 5.3 of Mil Standard 1530D explains that analysis is the key to both the damage tolerance and the durability of military airplanes. NASA Handbook 5010 says pretty much the same thing for space structures. Section 5.3 of the Mil Standard also states that the primary role of full-scale testing is to validate correct analysis methods. So why are we talking about Scalmalloy? Well, due to the exceptional strength stiffness to weight ratio, Scalmalloy represents an ideal choice for replacing aluminium alloys that are currently extensively used in both fixed and rotary wing airplanes, as well as in UAVs and in space applications, satellites, etc. And you can see that from this slide. This slide presents the crack growth curves, DADN versus delta K, for a Scalmalloy that has been produced by selective laser melt, SLM, and laser powder bed fusion. It also presents the corresponding curves for two commonly used aluminium alloys, 7075 T7351 and 7050 T7451, as well as laser powder bed fusion, commercially pure titanium that has been hipped. An essential feature of any DADT analysis is that a similitude parameter is needed both for the analysis and to ensure that lab test data that's obtained using simplified geometries under represented flight loads can be directly related to cracking in the operational structures. For the lab test data to be useful, the crack tip similitude parameter in the laboratory test specimen must have the same value as in the aircraft space vehicle. Otherwise, you can't relate lab test data to what's happening in the operational structure. This slide presents a schematic diagram showing the relationship between the crack growth rate, DADN, and the range of the stress intensity factor, delta K, in a given load cycle. There are three regions. Region 1, the near threshold region, where most of the life of an operational structure is spent. Region 2, the so-called Paris region, and Region 3, which is essentially rapid tearing. An important feature to note about this slide is that unfortunately, delta K is not a valid similitude parameter. What is meant by similitude? The common hypothesis is that if two cracks in two different geometries but the same material have the same value of delta K and Kmax, then both cracks will grow at the same rate. Unfortunately, this is not necessarily true. It only holds for long cracks in conventionally manufactured materials. The breakdown of similitude for conventionally manufactured materials is illustrated by the difference between the crack growth curves for short and long cracks. Remember, the small crack growth curve is the one that's needed for a durability analysis. You can see that in this slide. The small cracks, or the short crack growth curves, are basically straight lines, whereas the long crack curves have a sigmoidal shape. As an aside, a detailed discussion of the breakdown of similitude and the necessary similitude parameter for adhesives can be found in reference 7. Now, an essential feature of any durability analysis is that you need a similitude parameter. I mentioned before, both for analysis and to ensure that lab test data obtained using simplified geometries can be directly related to the fleet. By this, I mean that if two cracks in different geometries with the same material have the same crack tip similitude parameter delta kappa, then both cracks will grow at the same rate. Now, this definition is basically a modified definition of that given the United States Damage Tolerance Design Handbook. The similitude parameter delta kappa that I'm going to use in this talk is given by equation 2. It involves two parameters, namely a fatigue threshold term, delta kth sub r, and a cyclic fracture toughness term, A. The fatigue threshold term here is related to the traditional delta kth term, which you get out of E647 by the equation on the slide. With this definition of delta kappa, the crack growth equation is given by equation 1, which looks pretty much like a Paris equation, but with delta k replaced by delta kappa. This slide illustrates that if you express the DADN against the similitude parameter delta kappa, as in the figure on the right-hand side, then the anomalous crack growth curves that appear to arise when you express the DADN against delta k vanishes. In other words, all of the various long and short cracks curves collapse. We now know that for any given material, the DADN versus delta kappa relationship is independent of the manufacturing process, post-processing, microstructure, and the residual stress field. For 316L, it's been shown that for conventionally and CSAM, that's cold spray additive manufactured built 316L, there's a unique relationship between delta kappa and the change in the potential energy of the system. Mill Standard 1530 and EZ 1901 highlight the need to account for the variability and the isotropy associated with crack growth, particularly with additively manufactured materials. The paper by Jones and others highlighted how to do this using delta kappa. In this case, 26 different tests were examined, and we'll see the results on the next slide. In this slide, the figure on the left presents the crack growth curves for additively manufactured Ti64, both selective laser melt and laser powder bed fusion in different build directions, some of which are hipped, others not hipped. What you see in the figure on the right is when you replot that data against delta kappa, every one of those 26 curves falls onto a single curve. Having dealt with all of the preliminaries, let us go back and see how to characterize crack growth curve in Scalmalloy. Figure on your left is one we've previously seen. It expresses DADN as a function of delta K for Scalmalloy produced using either selective laser melt or laser powder bed fusion. In the case of selective laser melt, it's got two different R ratios. It also shows crack growth curves for 7050 T7351 and 7050 T7451. Okay. All of this messy curve on the left-hand side now collapse onto a single curve. This is true regardless of whether it's made with selective laser melt or with laser powder bed fusion. And you can see that this relationship holds for at least 4 orders of magnitude. Interestingly, the curve for Scalmalloy is very similar to that for 7050 T7351. What this means is that the difference in the growth rates that are seen between selective laser melt and laser powder bed fusion built specimens is governed purely by two parameters, the threshold and the fracture toughness. Let me try to draw this talk to a close. Scalmalloy appears to be an attractive material for additive manufacture of aerospace parts, limited flight parts, actual aircraft, UAVs, satellites, space vehicles. Crack growth in Scalmalloy we found can be represented as per the Hartman-Chivy variant of the NASCRO crack growth equation. The resultant DADN versus delta kappa relationship is very similar to that of the commonly used aluminium alloy 7075 T7351. The challenge now is to determine the curve needed for a durability analysis. This curve must account for the variability and the anisotropy associated with the growth of small cracks in additive manufactured Scalmalloy. This upper bound DADN versus delta K curve should lie very close to the DADN versus delta kappa curve given in the present talk. Why? Because for small cracks, delta K approaches delta kappa. This comes out of, or falls out of, ASTM E647, and you got to read Appendix X3. I hope I haven't put too much material in here. Are there any questions? I'd like to end by acknowledging my co-authors. And on that note, I'll ask for questions. Thank you very much.